with forecasting models, it's more common to talk about model risk and maybe the cost of assumptions. But of course, it's equally important, if not more, with causal models. So how should we think about it? And again, in kind of practical terms.
Yeah, I think in very practical terms, I would call it a range, right? The more money you're willing to spend, the less risky your assumptions will be, or the less risk you have that the assumptions you make are wrong. And if your assumptions are wrong, then your outcome, result will be possibly wrong and very misleading.
Jakob, welcome. Do you want to start by introducing yourself?
Happy to, yeah. I'm a PhD or finishing PhD at UCL in London, so University College London. In 2019, I got a DeepMind scholarship to work on causal inference. And back then, actually, it was for something called causal reinforcement learning. Nowadays, people call this general space just causal AI or causal machine learning. But I had the chance over the last 4 years to work very closely together with quite very interesting researchers in causal inference coming from the computer science side on tackling very fundamental questions, specifically about assumptions of causal inference.
Could you give an overview of how causal inference sits in the broader computer science space? Because I think often when you think about computer science, you don't immediately think about causal inference. So is it something that most computer scientists know about and care about, or is it more of a smaller specialty?
It's definitely a smaller specialty, but emerging. And I think in terms of computer science, really the biggest proponent by far would be Judea Pearl. So he did win, obviously, the Turing Award for some of his work. And in fact, Judea Pearl had won quite a few awards for superconducting physics before as well. So causal inference is actually something that he only really, doubled down later in his life. And I think it is the Book of Why that he published around 2018 that made the biggest shift. So he made this very, provocative statement of all of deep learning and maybe machine learning is just glorified curve fitting, right? And just because you fit a curve nicely into a space of observed data points doesn't necessarily mean that you have any causal understanding of the world. And right, there's a difference between taking an action and knowing what consequences has, so like a cause leading to an effect, and just describing the world, most simply of like, well, as temperature increases, so does the sale of ice cream. That doesn't tell me at all whether, ice cream sales make the sun go hotter or whether hotter sun leads to more ice cream sales. And of course, we know the answer for that. But so this is the classic example, and Judea Pearl has pushed for that. I think there is at least in his book or in one of his podcasts, there is this kind of revelation he had where he connected the Bayesian, the probabilistic graphs with causal inference. So that is his, one of his big contributions is the do operator. So a lot of times people clash on notation, for example, with the do operator compared to the classic potential outcomes, which comes from other fields that also mathematically characterize causal inference or causality, but that come from different motivations and just different way of thinking about it. In fact, we know that they're actually more or less equivalent potential outcomes in DAGs, but when it comes to computer science, you will find predominantly DAGs because directed acyclic graphs is a common staple in any undergraduate degree in computer science. And so that's why you will find that's why Perl goes with this language, and that's why people will talk about this. So a classic book would be, at this point, classic book 2017, Elements of Causal Inference, is predominantly written with DAGs, so directed acyclic graphs. And so I think this is where kind of like the computer science perspective starts, and everything else we can kind of derive from there, why people are motivated in the computer science flavor of causal inference to make certain modeling decisions or certain have certain ideas or expectations how to think about causality.
Going back to the potential outcome framework versus the DAGs and the do calculus, are there any differences you would highlight? Because, for example, as an economist, in my education in grad school, I never saw a DAG, I want to say, but then as I continued educating myself after, I've seen it in papers, and the first time you see it, it seems very appealing. It's like, this is very intuitive. Why do we bother with this potential outcome framework?
Yeah, absolutely. I think some people describe DAGs as something syntactic sugar. It's like very sweet. It's easy to work with. But there are some caveats with DAGs. For example, it's not as fully expressive as potential outcomes, and that's not necessarily very hindering for most causal inference modeling people do, but there is a technical difference. And again, there are these single world intervention graphs that connect the DAGs perfectly mathematically consistent with the potential outcomes. So they are mathematically essentially practically the same, but DAGs in a very, very niche kind of perspective are a little bit less expressive when it comes to independent statements about potential outcomes. And so I'm going to leave it at that for now, because anything else would require reading actually into this paper on single world intervention graphs, which personally I think should be one of the top 5 starting papers in causal inference. As I still now, again and again every meet people that say, I come from DAGs, what are potential outcomes? Or I come from potential outcomes, what are DAGs? And there's this huge confusion, and understandably, there are many books written in one or the other category that never mentioned, the other one. So once you hear about the other one, let's say when I heard about potential outcomes, I sat down and I read, Hernan's book on what if for 3 weeks straight, until I came to the realization, okay, actually, they are the same. And that's because I did read then the paper on single world integration graphs. And so I think the long story short, anyone that complains one is better or the other has missed the point of causal inference. I've met many, many economists who have said that learning about DAGs has been very enriching, but they're still going to keep going in POs just because, that's what they're familiar with. So I think it's the same kind of, let's put it on this level, the same as saying like a program in Python versus Julia or PHP instead of Ruby, it's just a matter of tools at the end of the day. Still now, obviously, with the very slowly but solidly emerging research of causal inference, we still have people that are trained just in one or the other. And there's going to be a lot of confusion still going ahead. But the key message is essentially the same. They're just a tool for expressing something about causality in one or the other language. And just read the paper on single world intervention graphs.
I'll obviously put link to these papers with the episode.
Yes, yeah.
It obviously seems optimal to have access to a wider range of tools, because in some situations, as someone who works in an applied business context, a DAG may be easier to explain identification assumptions, for example, to someone who's not a technical stakeholder, but should be understanding the assumptions we're making, because they, of course, carry some inherent risks.
Absolutely, yeah. And it's a trade-off, right? So, of course, a DAG, everyone gets it. But I think, for example, DAGs tend to suggest that the world doesn't have that much confounding, if you know what I mean, right? You just plot down all the variables, you connect them with the edges, and then you're like, here's my causal model. But the fact is that, realistically, most edges will still be confounded in some way. And so, once people realize that actually you can write down a graph with 10, 20, 100 variables, but it doesn't matter if your variables are confounded with confounding you can't measure, then people slowly become, more accustomed to the real challenges in causal inference. So maybe to just put something there that I think, is where things are going ahead. But it's like, DAGs are great. You can represent, ice cream cells and the temperature and more complex health scenarios, like long-term exposure to smoking and so forth, and how, your socioeconomic status plays into it, and your parents, and all these, 10 variables you can put into a system. But at the end of the day, most causal problems in the DAG space can be reduced to something called the proximal learning setting. And so that's that you have a variable X that's influencing a variable Y. Then you have confounders U, and then you have these kind of proxy variables that are pre-intervention and post-intervention, and they influence what the outcome and the confounder, or the effect, the cause and the confounder. And so again, that's proximal learning, something that's coming around now from Chetkin and Chetkin. And that actually is much more important to understand the setting than how, you can create a whole bunch of complicated graphs and so forth. Because at the end of the day, when it comes to the causal inference task, so you want to figure out an effect from X onto Y of temperature onto ice cream cells, you have to tackle confounding. You have to find methods and tools to, grapple with that. And the proximal learning setting is usually where you will end up eventually anyway. So as a caveat, DAGs are a great starting point to learn about it. Just as important is to come to a realization that you need these specific tools like instrumental variable models as well, which economists love very, very much, and proximal learning and so forth, to actually come to, reliable inference on cause and effect.
Could you maybe give an example that's intuitive or helpful to someone who sits and works on causal problems in a business on how to think about this proximal learning?
It's a good question. Let me see if I can quickly get the paper up, and maybe they can give an example there, because then it would obviously make sense.
Yeah, and you can obviously share your screen too.
Okay, let's see. Is there primarily people hearing and listening, or also watching as well? Because then sharing the screen.
It's going to be with video, so.
Proximal learning, this is from 2020, Eric Chetkin. And so we can look here again at the setup here, which is this one here. So we have a DAG with endogenous point exposure and proxies. So in this case, they have A to Y. I know this is a bit confusing because I talk from X to Y. But we have here the proximal learning setting. And so here in section 3, they talk about the proximal identification in point exposure studies. And so people might be already familiar in the causal inference setting with covariates. Confounders are sometimes also called covariates. And so in this case, we have X, C, and W. And so we see that Z is here on the treatment A. So A is the treatment and Y is the outcome. And so X is here a confounder or covariate that we have measured, whereas U is a confounder. And as you can see, it's going into Z and into A and into X and into Y. It's confounding everything. And so in this setting, it's confounding everything, including the confounder that we have measured, as well as these side proxies here. And so this is the proximal learning setting. And so when we're here, for example, search for example, you have here an example of confounding proxies in analysis of the causal effects of ART on HIV infection related to disease progression from observational studies. So I guess what we could imagine, for example, here in this proximal learning setting, and again, this can look in many different ways, but let's say we have some HIV outcome, health outcome, are you healthy or not? And then we have some kind of drug that we're administrating, A. And so now we have, for example, the covariate H. So H is usually, a big confounder or a, covariate with drug efficacy. So, the older you are, sometimes drugs works better, or sometimes the older you are, a drug works less so. And so X, in this case, could be H, and that's the confounder everyone is familiar with. But then we could have other confounders. For example, H could also be an influence onto Z, which might be your income, right? The older you are, it tends to be more income that you have disposable. And then this income here is also then influencing, maybe let's say what kind of drug you have access to and so forth. Whereas there might be also age might be influencing, let's say, your postcode. Maybe young people tend to live in cities and older people tend to live somewhere else. And then, of course, if you live more in the countryside, maybe your HIV, treatment health outcome is better because it's less stressful or something like that.
Sorry, and these are measured or unmeasured in this study? These are the measured.
Yeah, unfortunately, in this graph, it's not indicated well. So everything that I've selected here, which is everything but U, would be measured. But then we have this bad guy U, the bad guy in causal inference, U, the confounder, the unmeasured confounder, that is influencing everything here in the setting. And so as it is influencing everything here in the setting, depending on how crazy it goes, the causal inference, that you get even by adjusting, for all these confounders might still be wrong. Except that if we have knowledge that our measured variables are structured in this way, then we can actually apply the proximal learning mechanism and get a unbiased causal effect estimate. And so we can imagine that, of course, these might be single variables X, Z, and W, but in fact, also they can be vectors, right? So if I can separate, certain measured covariates, that they happen temporally before another one. So let's say X happens before W. Well, then now I can classify them here this way. And so if I have a covariate W that doesn't influence the treatment, well then, I can put it on the top right. Whereas if I have some covariates that don't influence the outcome directly, but are, a consequence of a confounder X, of a measured confounder X, and then they also impact, the treatment A, well, then they go into the group on the top left. And so that way you categorize your covariates into 3, groups. And then that way you can apply the proximal learning mechanism to then get a cause effect point identification. And so again, as you can imagine, this could be an all very complicated graph, with 10, 20 dimension, variables all around here with crazy, edges and so forth. Doesn't actually matter. It matters more what they look like in the proximal learning setting.
And in practical terms, suppose you're a data scientist and you want to calculate this causal effect. Does this paper provide any guidance on the formula? Is there a Python package, right? All of the practical questions.
All the practical questions. Yeah, so definitely I do come more from the theoretical side and tackling the fundamental questions. This paper, of course, can be read. And then, of course, that is somewhat more complicated. The answer is in the paper, and I think it's just 2 equations that are important. Long story short, I think there is already a package out there. So let's see, Causal Inference. Let's see if we can find something.
Yeah, and if you don't find it quickly, we can look after.
Yeah, so it should be available as a code, yeah.
So yeah, because the motivation of my question is that often you are working on a specific applied problem in a business, and the textbook method that you learned in grad school doesn't really seem to apply. So then you Google, and maybe you find a paper that's more recent research, but the step from reading the paper to actually applying it in your own work, even if you're someone who has a PhD and a couple of years of experience, is not always immediate.
Absolutely, yeah. And I think, to make this conversation more helpful in that regard, so definitely proximal learning is on the horizon. It's coming. It's probably not that established, it's something that, still, I guess, the theory people and the statisticians talk about. But it is something that will find its way into the textbooks sooner or later. So, for the current generation that has now the task of, sitting in a desk on econometrics or causal inference in a big tech, of course, what methods do you have disposable? And I would say something more like synthetic control, is much more tangible. And I think even Google has already a package out for that since 2014. And so the reason I know about synthetic control is because of a research internship I did at Spotify. And that is a method that I personally trust a lot in terms of the practical impact. And that is much more tangible because, it's been now 10 years since Google had a package on it. It's available for Python and so forth as well. So these are packages that, the theory behind it is also easier to understand maybe than the proximal learning package. And so, yeah, I think we're definitely looking at a range. And the way I think about that usually is that we have an adoption curve for methods, right? We have all the great ideas in the nascent stage. And then eventually someone, goes out there and makes a first, package for some people to use. Maybe it's open source, and then it gets some idea and someone promotes it maybe at a conference. And then eventually, once it's really in a textbook, it's made it as a method and it's part of the tool belt, As we talk, we can maybe put them like on the range where this method is. And so proximal learning is nascent stage, but I would personally argue actually easy to implement. So I would say proximal learning is something that is so easy once you understand it, you can implement it yourself. But of course, there's also going to be packages for it. In comparison to synthetic control, which is on the very other side, which is very, very established. So the packages there are quite accessible.
Is proximal learning applicable in both observational and experimental settings?
Yeah, I think my theoretical answer for that is everything is always applicable in some way. And so my mindset about this is that once you have experimental data, you can enrich observational data with it. Or to put it another way, if you have observation data, you can enrich experimental data with it. Now, again, we're talking about nascent ideas here. And so, yes, you can use experimental data to enrich also something like proximal learning. I think here, there aren't really many packages that I'm aware of that, that help, navigate the space of how to use both kind of data sets. In fact, I'm still finishing my code for a paper that is using both experimental data and observational data to do something called partial identification. So it's a subtask of causal identification. And so, yeah, so the mindset should be really like, how can I get them together in a good way? And again, this is a big task for someone on the applied side. And then I would actually just simply say, well, do maybe stick more to the separate task, observational causal inference. What does it tell me? And then does it contradict, for example, the experimental results I have? So this is the approach I would take currently.
Because of course the challenge is in many settings you only have observational data and you can't run an experiment. And then it all rests on the fact or the assumption, do you trust the DAG that you claim exists, right? Because we claim some causal structure and confounders, and then we claim that we're able to control for them to use whatever method it is that we use for observational data.
That's correct, yeah. And so it gets even worse, obviously, because once you trust a DAG, you still trust that your assumption on the relationships between the nodes also are of a certain type. So a lot of initial research in causal inference was assuming linear relationships. And that's actually quite nice because it has led to a lot of results that are very useful. And usually in research, you start out with the linearity assumption, and then you drop it to the nonlinear case. But for many cases where you drop it to the nonlinear case, it becomes much, much harder to defend. So yes, definitely, when you assume a DAG based on your expert knowledge, you want to have a good conversation, whether this is justifiable or not. And again, the test of science isn't, to have one opinion that's better over the other. It's to look at all the evidence and then to understand, which one is the most plausible theory and compare the theories as well, right? So we should be comparing DAGs, and then, this DAG A, it has a missing edge compared to my DAG B. What impact does it have on my, final result of the causal inference? And so, yeah, so we're not going to get around this ever. It's a fact of nature and a fact of life that you will need to make assumptions in science, and you will need to make assumptions in causal inference. Now, what do we do with observational data then? Well, we want to be reasonable about, how we analyze it and how we use it in our daily tasks and how it informs our decision making. So if it is the best you have right now and you are confident with your assumptions, then maybe there is nothing else you can do. And then that's just fine. But I think personally, I would always say there should be a mindset of how do we use this as a path towards experimentation? Because if you have absolutely no path towards experimentation, then it will be quite hard to justify your results. And then oftentimes you will find yourself in environments that will judge, your outcome based on anything but the statistical rigor.
Would you say if someone only has access to observational data, which would be, I don't know, how consumers react to a certain feature of the business offering, right? And so we could assume a lot of confounders and say we control for them and we do matching or panel data setup, whatever we do, right? Then depending on the sample that we use, we can run the model and we get a parameter estimate. We almost always get a number back. And so how do we have confidence in this number? One thing we could do is estimate it on different subsamples of the population and see whether the heterogeneity of the estimates that we get aligns with intuition, right? Maybe we do young customers and old customers, and we have some expectation of how they would react differently to this intervention. And then if we get an estimate back that's in line with intuition, we're happy because we feel more confident in our method. And if we get something back that is nonsense, then we start questioning it more. Is that a good approach?
Well, I mean, this is where it shifts from academia to the practical space, right? In the practical space, you have deadlines and you will cut corners because you have deadlines. That's just the nature of it as well. So maybe one story I can share is, for example, that someone, came to our research group at UCL and was sharing data on, I think, a certain disease, a treatment for this disease. I think it was in the developing countries, a certain kind of vitamin was missing. And, with that vitamin, I think the idea was that the children, mortality rate, infant mortality would be reduced. And so they had the result that when they looked at the observational data of, this kind of vitamin use, they would see that actually infant mortality rate, I think, increased, but for male infants, not for female infants. And so that went entirely against the intuition. And in fact, I don't know the outcome of this, but the result was effectively that they had this statistical result, that this drug actually makes things worse, but they couldn't pinpoint what it was that was so going against the intuition and what they would actually see, in reality. And so the same way, when you say, well, you can do some kind of test of my method or my model of my setup, but checking whether it matches my intuition or not, well, then you've already introduced a bias, which is, your intuition or your assumption of what the world should be. And so if that is acceptable at, where you're working right now as an approximate measure of, whether something works or not, then I guess that's fine. But technically it's problematic, right? Because I think with all the, trade-offs we make and all the shortcuts we take to meet a deadline in industry, you never want to forget the, limitations of causal inference that come from theory, which is that your assumptions, need to be validated. And if they're not, and if they're violated and you don't know about it, then your result is going to be wrong and misleading. And so my recommendation is simply to have, maybe several models with weaker and stronger assumptions available. So, a really weak one, a really medium one, a really strong one, and see how different assumptions impact the result and the outcome. And, that should build much more confidence. And I think we all introduce some kind of bias once in a while, especially in a practical setting. But I think it's important to, when you cut corners, to at least take a note, what the consequences are.
Maybe this is a good segue into talking about the cost of different assumptions. Because of course, in a business setting, we typically want to tie our projects to a dollar value in terms of impact. And often we focus on the final end product, what value that product would bring to the business. But of course, the end product is based on all of these assumptions that we make in the modeling phase. And I think with forecasting models, it's more common to talk about model risk and maybe the cost of assumptions. But of course, it's equally important, if not more, with causal models. So how should we think about it? And again, in kind of practical terms.
Yeah, I think in very practical terms, I would call it a range, right? The more money you're willing to spend, the less risky your assumptions will be, or the less risk you have that the assumptions you make are wrong. And if your assumptions are wrong, then your outcome, result will be possibly wrong and very misleading. And so the most drastic opposites are, is a complete observational study where you just, make some very convenient assumptions because you can use a package in RStudio compared to a rigorous experimental clinical trial in pharmacology, right? And so you have this whole range. And of course, most businesses aren't going to do FDA-regulated clinical trials like AstraZeneca or GSK are doing. But some businesses can afford to do experimentation, when they have a certain size of users. And that's what we see in Uber, in Netflix, and in Spotify as well. And so these are the classic A/B tests, right? Once you reach a certain size, you can do that. Zalando has a big team as well. But Netflix are really, really nailing this space. So they have very sophisticated experimentation algorithms. And they come at a cost, right? So billions, maybe, I don't know, millions at least, but possibly, depending on how much it costs to run these experiments, it would be billions. And the result is a very low risk, high reliable outcome, what kind of movies to promote or what kind of shoes to present in what way to engage the customer more. Now, everything below experimentation is obviously much, much cheaper, right? So we just need 1 or 2, maybe 3 full-time people that sit in a room, talk to each other, once in a while reach out to an expert, and then make a decision what assumption is good and what assumption is bad. So the risk there is obviously that you're only looking at observational data and that biases can creep in and that the results aren't reliable. And then when it comes to decision making, right, you want to make you want these results to be actionable, that you making decisions about a product or a business model that is just wrong. And so that is obviously when you've underinvested into validating these assumptions. Now, I think there's no escaping in observational studies, that you're going to have results that are going to be not reliable. But it is really at the fringe of observational studies, when you can go out and do some testing, that you really should put down the money to do some testing. And I think testing should always go over observational studies. Now, when you are then, again, in a just purely observational study setting, let's take public health, the Harvard School of Public Health, Miguel Hernan spends a lot of time just thinking about assumptions. Classic assumption is, something called monotonicity. In the drug setting, it means that, this drug can only ever improve things, but it will never make a patient worse. Very powerful assumption. It halves your solution space. And so therefore your results will be much more reliable and you can use many more causal inference methods. But that's possible because they can query experts and they can look at, patient case studies and so forth. So when it comes, I guess, for the whole range, at the very, very, left, you have, I'm going to hire a data scientist that hasn't done causal inference and is just applying packages. That's very cheap, but you're going to have eventually problems. And those, you will start distrusting this person just because they don't have the tools and the time and the training to get reliable results. Then we go up to someone like Miguel Hernan in the Harvard Public School of Health. They are funded, with millions of US tax dollar, money, and they will present observational results that are very, hard to argue with because they spend so much time in it, and they're also incentivized to give you results that are, good for public health because that's what they're interested in. And then we get to, the range of industry where you can afford to do experiments and where you do put down the money, and that is where we get these huge A/B testing trials. And of course they impact whole businesses, and the whole business has to support that, and that comes at a cost of millions. And so that's kind of my range of like where things are, and we have this, very sharp cut in the middle where you jump from observational to experimental studies, and you really want to aim for that always, just as a matter of rigorousness. But when you're down in the valley of observational studies, life is harder. But even there, you can make a big difference, by hiring someone who knows how to do these things, getting a consulting expert in who will look over a report, and not just having someone, that doesn't have the tools yet or the experience to create observational studies.
And as someone who is an expert in causal inference and sits somewhere at a tech company in a setting where there isn't an experiment and you only have observational data, I guess part of your job should be to, as you produce your results and you show them to your stakeholders, very clearly explain that these are the assumptions I am making because I only have observational data. And these are the risks of these assumptions. And the only way to fully validate this is to run an experiment, to really highlight that.
I think in a nutshell, that should be in those reports. And I think it's also a matter of industry standard, to be honest. If you go to your manager and you give them a report and every time it has these 3 pages of disclaimer at the beginning, they're going to be like, well, what is this? Like, this is annoying. I don't want to read it. So I think we should have some kind of industry standard of like, this is a observational study in causal inference in an industry setting, caution because ABC. And there should be, the same, expectations at Google and Spotify and Zalando and so forth about, these results. And that comes down to manager training as well, right? I've heard too many stories, of managers saying, I don't like these results, come back with something else, right? That's not okay in terms of statistics, but it happens, right? And so I think for the field of causal inference to, have a healthy future, the data scientists will have to hammer down these points. And I think that does include, 3 pages, put it in an extreme way, 3 pages of disclaimer every time you release a causal inference report, just to, for the next couple of years to make clear to people that this can be very helpful, but it does require a careful treatment of the assumptions. So yeah, I would agree with that. And it would be annoying to some managers, but that's just the nature of it.
Yeah. And I also think it comes with seniority. The more experience you have, the more you realize how uncertain things can be, right? Like undergrad students stick data into a package and get a number back, and they think that number means something, and they haven't even looked at the data properly. But I think when you have more experience, you're much more comfortable advertising all the uncertainties of the result you're presenting.
No, it's true. It's true. I agree with you that actually surprising to some people, especially undergrads, oftentimes the less certain a person is, so the more careful they are to make conclusions, the more seniority you're actually dealing with, right? And definitely, of course, it's fun to take sklearn and get some results out of it in numbers or A/B test results. But I think that the true rigor and, almost the art of the exercise is to know when your numbers aren't reliable. It's not to produce the numbers is easy. to have numbers that are reliable is much harder. And I think maybe one story here, and this is really, it's really a incredibly important book, is Ronnie Kohavi's book on experimental design of Bing. So he was leading for many years the development of Bing, the search engine of Microsoft. And so he would say that, even when running A/B trials, A/B tests on certain features and so forth, it would only be maybe, I think, 2 or 3 times a year when they really would get a big signal enough to confidently say, this is a good feature. And that's in, experimental studies. So when it comes to observational studies, it's obviously much, much harder as well. So I think really knowing when to step back and when to say, maybe we just actually had, I don't know, a public holiday in China that screwed our results, being able to, being confident enough to say that these results just are no results is incredibly important. And I don't think this should be like a blank check now for everyone to say that, I don't know if this is true or not. But I think we will also learn how to differentiate, for what are, good results and bad results as a community as a whole over time. And so that requires, a conversation and standards again to think about that. So yeah, I agree with you. So undergrads should more importantly learn, the failure modes. And I guess, that does come with experience eventually.
One topic where I often find myself thinking about causality is in the context of forecasting. So there are many, many places in the business where we need to forecast something in order to make a decision, right? Like the demand to stock warehouses and financial projections and so on. And I always ask myself, how much do we care about causality here, right? Like it seems like we should care quite a lot, because often to make a good forecast, right, basically either we have forward-looking features. So for example, we have future levels of the state of the economy or promotions or something like that we forecast. And then we use them to drive our forecast of demand or whatever it is, right? And in that case, it seems we're making an implicit causal assumptions, because if we didn't think those features are causal, then why would we even use them in the first place? Or we have a more boring forecasting model that just relies on the past, right? And then we kind of hope that the past repeats itself to a certain extent. But I don't often find people discussing causality in forecasting teams. So how should we think about that?
As you raise this question, I also find myself not actually talking about this much. So I think on the one side, as I mentioned before, a correlation model, something like ice cream sales determine the temperature, that's obviously not true, right? We know that the temperature determines ice cream sales. So if I'm running my ice cream stand, I'm going to be tracking temperature. And then if I see a projection that next week it will, get really, really hot, I'm going to stock up on ice cream, right? So that's a pattern that is reliable in business, I guess, to stock up on. And so the causal model, in a sense, of course, should help with that if, you could predict, I guess, interventions in the future as well. Long story short, I guess in theory, this should be something that people connect. And I think this is also, again, where the difference comes along, again, from computer science and econometrics, maybe, because I think econometricians tend to think, about the future state of the economy. With computer scientists, they think about, I have this data, I want to make predictions, and then I want to also make maybe predictions about interventions. But you don't tend to, in a causal way, think about forecasting. I think what I'm maybe going to introduce here is that you don't necessarily need causality to do forecasting. So for example, the climate change models, they can actually be done without, a substantial causal understanding of the world, as far as I know from some work I've seen. For example, there's a method called Gaussian processes, and you can tell them, these Gaussian processes about seasonality. So we do know that the world has seasons, right? In the winter it's cold, in the summer it's hot, depending on where you are on the planet. But you can actually just tell, the model that there is, a sinusoidal relationship, so it goes up and down. And then you can tell it is, sinusoidal linear, so it goes up and down, but in general, it's always going a bit up. And so that's the climate change model, right? That, temperature is increasing on average every year. And that doesn't necessarily require a causal understanding. It's a, relatively reliable prediction machine. I would also argue, that when it comes to forecasting, I think everyone's trying to really do like the stock prediction game at the end of the day, but harder versions of it. So like, the stock market is inherently incredibly volatile and hard to predict, but once in a while some statistical patterns do emerge and they can be exploited for making money and exploiting arbitrage. And of course you could do that in logistics as well and so forth, but I think maybe the information exchange isn't strong enough. Or when central banks make predictions about the economy, I always find it very problematic. Maybe the best answer I can really give there is in terms of synthetic control. So that's the closest I've come to like a causal understanding of a forecasting model, because in synthetic control, you also predict, let's say, for example, you want to understand the impact of German reunification on West German GDP. It's a classic econometrics exercise, classic synthetic control example. So what you're trying to do is you're trying to predict German, West German GDP as if nothing happened. And so that is a retrospective forecasting, right? Because you have at that point already seen other countries, but you're still like predicting Germany as if it was that way. And so you can then use, for example, Bayesian methods to extend this model also into the future and then say, I want this uncertainty to increase, by this certain rate. And so what you will get then is a forecasting of whatever economic, indicator you're interested in. But the uncertainty increases so rapidly that, it becomes very fast, very useless. So long story short, I haven't thought about this much. I agree with you that there's some terminological, conflict that hasn't been resolved. I think in theory, of course, intuitively, it does sound like causal models should fit into this problem space, but I haven't been able to make that connection myself yet.
So you mentioned computer scientists don't typically think about time series in the way econometricians do. So in the group of computer scientists who do causal inference, what types of applied problems are you interested in?
It's a good question. I think, first of all, there is actually quite a lot of work on time series coming up. So there's, for example, a workshop on time series at UAI. So that's the Uncertainty in Artificial Intelligence conference series. They're having a conference next month in Barcelona. And one of the 3 workshops is on causal inference for time series data. There are, of course, also econometricians involved with that, but there is also a climate change researcher here. And so I think it's wrong to say that they're not interested in it. I think people are always interested in it, and it's a matter of what's the fashion right now. But what are applications for computer scientists that do causal inference? I think we need to differentiate between where these things are actually being used, and then what are the classic, retro examples that are used in papers. And I think there's simpler ones and there's more complex ones. So maybe let's start with the simple ones. So I think synthetic control, even though it does come from econometrics, I think, it is being used in big tech to look at, impacts of user behavior on platforms and stuff like that. So when you don't have randomized data, you can use that there. And synthetic control is incredibly simple, relative to other methods. But then computer scientists maybe look at the biological space. So you might have protein networks. You're trying to understand an intervention on one node, protein, maybe a knockout and something like that on the remainder of the biological system. So that's the paper, for example, from I think 2005 that looked at a causal discovery method, so learning the structural graph for I think a certain type of fly, or a certain type of fruit fly. And they did actually figure out some genetic graph connections there. It's a classic. I think it even got a test of time reward recently. Then from biological space, we can also go into the climate change space. So you want to understand, how certain weather behaviors have a causal effect on other weather behaviors. There's actually very predictable, storm behavior across the Atlantic, I've learned, where, you have the equator and certain storm formations appear again and again. You understand the connections between that. I also have seen someone apply to the sustainability goals, the UN sustainability goals, some kind of causal structural learning. Although that's obviously, as you already said yourself, very hard to do when it's just observational data. So long story short, there's a lot of academic ideas on it. I think in concrete applications to industry, things tend to be watered down to more simpler methods just because they're easy to understand and to communicate and work with.
So you mentioned causal discovery, which is something I would love to learn more about and where it's applicable. From my very limited understanding, right, it seems like something that would be doable if it's a closed system, right? Like you have a fly and there's, I don't know, no outside factors that affect the proteins of the fly. But how would it be applicable in a business context?
Well, two questions. How does it work? Well, you make some assumptions. So maybe just, for the newer listener, causal discovery helps you find the graph. Once you have the graph, then you can find the effect. So sometimes people think that causal discovery is the first step. Sometimes people skip that step because they're so confident in the graph. Generally, for some reason or the other, the structural learning, so the learning of the graph, and the point identification have been treated separately, and people have spent their PhDs doing only one or the other. And that's just the way things are. So again, there might be some confusion that these are two different things. In fact, they also have the mathematical same fundamental basics that allow them to make results. When it comes to structural learning, the task, we have to make also assumptions about, independence or nonlinearity or additive noise. There's all kinds of mathematical tricks. I maybe, to make it more honest, there are mathematical tricks where if you assume, if all the noise is additive, then you can use a certain algorithm to give you a certain graph. And I guess I'm going to mention one thing here. For example, there's this package called Causal Nex. I think McKinsey developed it, Causal Nex. So there's Causal and then NEX. It's still being maintained by McKinsey, and I actually went to one of the talks in 2019, I think, and they were showing halfway through for the talk, they showed a slide with 100 variables, and they said, we take this to our client. This is something you offer as a service, and then the client, tells us what's wrong with the graph, and they're like, this node actually doesn't look like this, or that node should look different, and here's a missing edge, and so forth. And I still find it now a bit confusing that you would, present this as a service when you then go to your client and have them correct the graph you made. And so I think there's a confusion, that oftentimes people look at these methods and they're like, oh, the graph is going to come out, and like either they think it's correct, which is very problematic, or they're like, this is some basis I can work off, or, this has some information that's useful. I think there's so many different structural learning algorithms out there that lead to different results that it's really important to know what they can produce instead of just taking results. So long story short, I think this is going to be hard to make really practical in the business setting for an applied user. And especially if you get into this kind of senseless loop where, you create a DAG, you take it to an expert, they make a whole bunch of corrections, and then you look at it and you're like, wow, this is great. I'm sorry, but at that point, just go to the expert and have them, create a DAG, and then maybe look at if it's statistical valid or not. So it seems like an extra cool, fun, fancy exercise that doesn't have any business value because the expert already knows, most of the time how the DAG looks like. And so that's kind of my opinion on that. And I mean, the story is that, McKinsey doesn't pursue this further because I think they also have, seen in some ways that this is a ridiculous service to provide because, the customer has their own opinions. And that's one part of that story. Does it have value? Well, let's connect it to what I said previously about proximal learning. Yes and no. It does have some value to look at this and to analyze the results in the context of how they were produced with different algorithms. But at the end of the day, the most reliable observational causal inference you're going to do is still through classical approaches like the IV model or proximal learning, where the DAG is being reduced to a more simpler problem anyway. Because the truth is, point identification isn't about the network of 100 nodes. It's only about the cause and effect and what confounding factors you have and how they're related to each other. And so having a DAG with 100 nodes and, printed out on a big page, it doesn't help. It doesn't help with your problem.
It sounds like maybe it would be helpful if you have, I don't know, a factory with some complex system of machines that interact in some way in the manufacturing process, and there's an error somewhere and you don't know what causes it, right? And maybe for some reason it's impossible to have an expert look at the sequence of machines and something like that. I don't know. But not in this context that we often work with, right? Like a consumer is exposed to a marketing event. What's the cause of that?
No, that's totally fair. I think you're right that, in fact, if you do go and you look at, okay, so, and so, for example, I know that someone's applying structural learning as a root cause identification at ASML. I think they call it ASML. ASML? Yeah, World Supply to Semiconductor Industry. ASML is a monopoly that provides all the lithography machines to NVIDIA and TSMC and so forth. When they have a complex system of machines, that the expert has limited knowledge about, they are trying to apply causal inference. And that is maybe one of the very niche cases where it does make sense to get an additional graph, with 100 or 200 nodes, that gives some hint to where to look towards to. That is absolutely fair. But in the classic big tech causal inference, fancy whatever setting, these graphs, need to be taken with a grain of salt for how much value they provide. And it comes back again to the question of what is it? How are you going to explain it to your manager, right? Are you going to provide the value of like, my machine found this cool graph? Or are you going to provide the value of like, I have these results that are statistically reliable in this way, and they suggest that we should go for this action? And those are two very different outcomes.
So going back a little bit to the economist versus computer scientist training, I actually recently spoke with someone who is a hiring manager at a big tech company, and he said he runs into issues finding economists who have enough coding skills, quite frankly. And of course, computer scientists have more training in coding. Are there any aspects of that training that you would highlight that you think economists who aspire to be really, savvy in that space should have?
Yeah, I guess I can give some recommendations. So I think number one, solid mathematical foundation helps with all of these problems. First of all, understanding papers, and then second of all, the programming as well. Now, just knowing maths doesn't save you when it comes to programming. There's a lot of mathematicians that are great at what they do, but they're not experienced in programming. And I think really it's a matter of training. The same way, if you train to play piano, you're going to have to practice every day. And the same way, I don't think as an economist, if you're serious about, getting maybe one of these great jobs, you want to think about a training as well. 1, 2, maybe 3 hours a day. You start, of course, with a, let's say, beginner course in Python, but important, you want to set yourself then, realistic goals for what you can achieve and what you're going to do on a daily basis to become better at this programming skill. It's a skill that's trained just like running or cycling or something like that. And so that is my recommendation, to not see it as a 3-month course that I take at the end of my undergrad or PhD. That's not going to give you the depth that hiring manager, you say, would be looking for. A hiring manager, after a couple of hours, would be able to see whether you just have some routines at the top of your head because you took a 3-month course, or you have a deep fundamental understanding because you've been programming for 2 years on a daily basis. It does just show through. And so I would definitely recommend, get the fundamental Python understanding. And then, of course, as an econometrician, you want to look at the, kind of data science stacks. So really get familiar with pandas, with NumPy, and do run your first kind of own personal project. And I think the great thing with statistics is that even on a PhD level is often underestimated. You don't need real data. You can create your own data in a simulation. You can program that up, and then you can do your analysis. Program a bunch of functions that simulate, 10-year-olds buying ice cream at the corner in Philadelphia. And now create that, data and then analyze that data and look at how seasonal influences, influence the sale of ice cream. You can do that all in your home, and you can do that, in a Google Colab. You can set that up and you can play and challenge yourself. So this is not a limiting factor. The limiting factor is really more how much persistence you have, to put in that 1 or 2 hours every day. And then that will shine through. And it's a long-term investment. It's not something that comes quick. But this is my recommendation as someone, from computer science, to be like, no one's learned programming in 3 months. No one's got to that level that they're looking for. But everyone that has, got that fundamental understanding has got there because they've done it for years and years. So,
of course, recently we've had big changes in terms of how we use AI in our daily work, quite frankly. Do you see, and there's this term causal AI. Could you, I guess, explain what it means and what you think about it? And also how you see, and if you do see the AI and LLM space merging with causality, and it's so what the things to think about and look out for are and learn about.
Okay, so two questions again. Where does a causal AI as a term come from? And second, where does it, I guess, go in the context of LLMs? So the term causal AI, as far as I understand, was a marketing trick generated to create the Gartner hype cycle curve. So causal inference is not a word that would have looked nice on the Gartner hype cycle, but causal AI is beautiful to look at the Gartner hype cycle. So if you look at the archives, you will see that people have come up with this term simply for the fact of marketing. Causal AI is simply causal inference, and then strictly speaking, causal AI is most likely when people talk about causal inference using a bit of machine learning. Now, there's also methods to do machine learning, and they use causal inference or causal paradigms to improve the machine learning. That is much further away from what people actually do in industry. The term causal AI is a marketing term that simply says machine learning and causal inference. That's what it is. And so, of course, people that do machine learning and or causal inference, are invited to work in causal AI then, because you can take up one or the other and make a contribution. Where does it fit into the bigger, room of recent changes with LLMs? Well, I think there have been a couple workshops on, how LLMs and causal inference would work together. And I think one question was like, are LLMs causal parrots? And I think, of course, you will still find proponents on both sides of the equation. So one saying, yes, they can do causal reasoning, and others saying, no, they cannot. I think, at least from my network, people are confident at this, point to say that LLMs have no causal understanding of the world. For example, you can ask it, a rigorous amount of causal questions about, does, temperature influence ice cream sales? And it will correctly, answer them, but you only have to change a few words. And for example, you can ask it about DAGs from X to Y, and then you change the X to a B or a T, and suddenly it's unable to do it because, surprise, or not surprise at all, it doesn't learn the causal relationship. It learns simply the linguistic, distribution that has been used before. And so that's actually, in a sense, funny, because LLMs tend to think about X and Y, as cause and effect problems, simply because most people use X as a cause and Y as the effect. But it has no understanding that X actually influences Y. So there's also, I think, some workshop papers on that. So that connection there can be made. There are other angles how LLMs can be combined with causal inference. There's a myriad of things people can do. I think the most central question is obviously, do LLMs have causal reasoning, or can we infuse causal reasoning into LLMs? And I think these are still open questions. Personally, I'm not a big fan of LLMs anyway. I don't use them actively. I know other people in the creative sector use them, and I think it's great what comes out of there. But I think for the more harder tasks that I face at a daily level, that there hasn't been value out of it. Yeah, so I think these are the two answers for that. So causal AI, in a sense, is a misnomer. There's not much AI in most of the causal AI that's being done. It's just causal inference. And then sometimes it's causal inference where someone switched out an estimator with a machine learning model. So that would be Victor, Jakob, and these kind of things. Or causal forest, you use a random forest for your estimation in your causal inference task, just so you can have these high dimensional data processed in the causal inference setting. And they definitely have their place. But that's just causal inference with machine learning. That there's nothing causal AI about this. It's causal AI is simply, to put it very cynically, a term to get your company on the New York Stock Exchange and get the most investment for that. There's nothing more than that.
No, that makes sense. And this obviously highlights how sophisticated we as humans are in terms of reasoning about causality. So maybe a closing question. Do you find your training in causal inference useful in everyday life?
Absolutely. I think one of the most wonderful realizations personally I have, and I think also for others, is the ability to think about confounding. I think in school you learn about correlation, right? And sometimes you learn about correlation. That would be already a luxury. And then you learn maybe about statistical prediction models. And then if you actually study it and do a degree on it, and you have a job where you have to build these models, and then you suddenly realize they break and they don't work, and you're like, what's going on? And you realize there's always these confounding factors. Then in personal life, you can also think about, oh, I made this mistake. Why is that? Oh, because there was a confounding factor. There was something else going on that made me perceive a relationship that actually wasn't there about the world. I don't know, finance, or, even with friends and so forth. And it's also important to see how, sometimes causal things break down. Sometimes, I guess if you're building your business network, and, oftentimes you're like, I know this person, but they know about causal AI, and why is that? And then you're like, oh, it's because we both follow this person on LinkedIn, right? The common cause is a person that posts about causal AI. I read it, they read it. And then when we talk to each other, we realize, oh, we have this common source of information. So this is where I see it in daily life very useful. It's just, and this also comes back to what we said about generally results and conclusions, right? I think we do live in times, of course, where people prefer to make, fast conclusions than actually suspend judgment, due to the lack of evidence. And so if people would just take a step back and be like, well, but what are the confounding factors here? Like, I don't know, this person insulted that person, but actually maybe there's a confounding factor, that there could be something going on in the background that we're not aware of. Global politics, local finance, Amazon selling things. Like there's so many confounding factors that we often miss that would explain, things that are confusing or scary or frightening, something like that. So this is the way I see it. I think, it's still on a daily basis. I suspend judgment. I'm like, well, I could come to a conclusion, but there might be a confounding factor. And more often than not, a confounding factor does, reveal itself later in time. I'm like, oh, well, that explains it. So, yeah.
I think this is a great closing thought. Thank you so much for coming on.
Yeah, thanks for having me.